I'ma call a couple of hard pipe hitters to go to work on the homes here with a pair of pliers and a blowtorch. You hear me talking, hillbilly boy? I ain't through with you by a damn sight. I'ma get medieval on your ass.
Okay, before we look at specific cases, I want to give you the generic form of electrophilic aromatic substitution. Each of these reactions will follow the same basic steps. The only difference between any of the electrophilic substitutions we're going to talk about is what it takes to generate E+, the electrophile cation. That's the only difference between any of them. So we'll spend a lot of time on how to make those in individual cases, but once we've done so, the aromatic substitution is actually very simple and direct. The pi bond from the aromatic ring will break, attacks the electrophile. Now there's the point where our new bond is actually formed. After that, you'll notice that we're left with a cation in the ring and an extra hydrogen on that carbon where the electrophile is now attached. The way that we regenerate aromaticity is something has to act as a base to pull that hydrogen off, reform the pi bond. So overall, what we have here is an addition followed by an elimination. That's what the two steps really are that make up aromatic substitution. It is an addition-elimination process, which we call substitution. But the same reaction is going to happen all the way through for the sulfonation, the nitration, the halogenations, the Friedel-Crafts alkylation and acylation will all go through the same pathway. Pi bond breaks, attacks the electrophile, some base comes in, regenerates pi bond. We get back our aromaticity with a new group attached to the aromatic ring as bonus. Let's take a look at the nitration reaction. This is a useful trick. We can actually put a nitrogen directly onto an aromatic ring. We put it in as a nitro group, the NO2, but we can actually convert that later to NH2 or as an amine or to amides, which we'll talk about in later chapters. This one is the longest as far as generating the electrophile because it involves a couple of different steps. First, if you recall back to organic 1, we talked about the idea that acidity and basicity are relative terms. So this is a good example of that. Here we're looking at nitric acid and sulfuric acid. Sulfuric acid obviously is the more strong of the two. It acts as an acid. Nitric acid is the weaker of the two. So in this case, it actually is going to act as a base. And you can see that here. Protonation of nitric acid. Now, I bet you never thought you'd see that in general chemistry. Nitric acid as a base. But, as I said, it's a relative term. Once that happens, you'll notice that we have two cations adjacent to each other. One on the nitrogen, one on the oxygen. Well, it doesn't get much more repulsive than that. They're going to fight each other off tooth and nail. And so, the covalent bond between them is therefore easily broken. It's favorable. It undoes the repulsion. Although an atom that was polar to start with stays that way. You'll notice the nitrogen still retains itself, it still retains the cation, a positive charge, even though it's lost the leaving group. That's because of the protonation step. So it began as a nitrogen plus 1, ends up as a nitrogen plus 1, and so here's our electrophile. Here's the group that we're adding to the ring. Here's the electrophile, the group that we're adding to the ring with the cation on it. Now the mechanism looks similar to what we've seen before. The aromatic ring will attack that. Because of the pi bonds to oxygen, it has a pseudo-leaving group. 2 electrons can go out, giving the nitrogen room to form yet another 4th bond, breaking one of the oxygen pi bonds and giving it back the original zwitterionic state that it had to begin with, where we had a negatively charged oxygen right next to a positively charged nitrogen. So after this, as before, we have something has to come in as a base. Well, we know sulfuric acid is not going to do it, nor is the hydrogen sulfate anion. A good candidate here, though, would be water. We lost water as part of the nitric acid to nitro cation, so we could use that as a base. Now, we reasonably have seen that many times. We've seen it form the hydronium ion where it acts as a base, so it's not a big surprise it can manage it here. As it does that, it regenerates aromaticity, end of story. Nitrobenzene and the hydronium ion, which is the aqueous form of the H+ that we started out with the two. All right, the sulfonation reaction. This one allows us to put a sulfur on an aromatic ring as a sulfonic acid, an SO3H group, which we can then later convert to thiols, thioethers, or even potentially use as a leaving group. So we're going to have a good bit of use out of this reaction in the long term. Some of it we talk about in this course, some of it is later, but the principle of putting it in place is very simple. We're starting with sulfur trioxide, a neutral compound, and sulfuric acid. Now, as we talked about in the past, sulfuric acid has only one job in life, and that's to protonate everything in sight. In this case, it's going to be premixed with SO3, so we're actually going to end up with protonation of sulfur trioxide. When that happens, you notice we have the SO3H group that's going to get attached to the ring eventually as a cation. Well, that's the big core. Again, we have to generate the electrophile, then we can add it, electrophilic aromatic substitution. So once we've generated it, we dump in the aromatic ring of question, in this case just benzene. The aromaticity is disrupted when the pi bond attacks the sulfonate. Fine, we can get away with that. The pi bond between sulfur and oxygen is broken as the aromatic ring attacks. We now have a sulfonic acid compound, but we have a cation left in the ring. Now the question here, your book sort of avoids the question, is what can act as a base here to take that hydrogen off and regenerate the aromaticity? Well, if you look at what happened around you before this, SO3 acted as a base. Why couldn't it happen again? It does. If we show this, SO3H acting as a base, we see the regeneration of aromaticity, and we have the active electrophile formed for the next step. How might you suggest that we could prove this was the way it works? Any ideas? Well, the best way would be to say, well, if I'm not using all that much sulfuric acid, then in the mechanism, then maybe I can cut down the amount in the reaction. The way that it's drawn here, sulfuric acid only needs to be present in a very small amount. Not strictly a catalyst because it itself is not regenerated, but in a non-stoichiometric amount, meaning it's not in a 1-to-1 ratio with anything in the balanced equation. Very small amount of it will get this process started, and then the reaction will carry on its own. Now, that doesn't mean we can't speed things up a little bit by adding a little extra, but hey, if we didn't have much of it laying around, or we have a limited budget, it's not necessary to have a lot of it present. It still works to give you sulfonic acids, which we'll use to a great extent a little bit later. Let's look at the halogenation. The way that we do this reaction is we use a Lewis acid with the halogen, either as a gas for chlorine or as a liquid for bromine. And what has to happen first is the formation of a Lewis acid, Lewis base complex, which I've got shown here. You can see that the halogen attacks the iron. The iron is a Lewis acid. We end up with a salt. Well, that's going to behave as if it were the halogen as a cation. It's not exactly that, but it's heavily polarized in one direction because of the attachment of the metal to one halide. So the other one is accessible and very polar. It'll behave as if it were just Cl+ or Br+. After that, it fits right into our generic mechanism. The aromatic ring will attack that, give us the attachment of the halogen. Now we have to get rid of that extra hydrogen. As before, something has to behave as the base. The most likely candidate here is this complex, the iron tetrabromide anion, where formally we have a negative charge on the complex. In reality, it is a negative charge on the iron, but the extra electrons are on all the bromines. So what is thought to happen here is the iron complex attacks that hydrogen as a base. Simultaneously with that, one of the bromines, the attacking bromine, is jettisoned from the iron. So in the course of this reaction, what's actually generated is HBr. And the Lewis acid is regenerated as a catalyst to be reused. And we can prove that part because we can use less than one equivalent of it. We can use down to like 2 or 5% of it, which is nice because it's hard to handle and it's relatively expensive. So the less of it we have to deal with, the better. But the point of this is we know it's a catalyst because we can decrease the amounts and the reaction still works. That's quite common when we go to study reaction mechanisms. Is we'll see something that does not behave as part of the rate limiting step, does not behave as part of the stoichiometry, does not behave as if its concentration really affects things that much, and then we leave it out and nothing happens. So the answer then is that we don't need all of it, but we need some of it, and it's probably a catalyst. In this case, we can see that clearly. The reaction works whether you're doing either the chlorination or the bromination, but what you want to do is make sure that the Lewis acid matches it. So you'll either use iron chloride if you're using the chlorination, you'll use iron bromide if you want to do a bromination. Alright, so far we've managed to put halogens in place, a sulfur in place, a nitrogen in place. We can't easily put an oxygen directly in place, but we'll look at some indirect methods of doing that another time. We haven't addressed the big question of organic chemistry. How do I put a carbon there? Well, the reaction that's used to accomplish that is called the Friedel-Crafts reaction, and there are two variants of it. The first one is called the Friedel-Crafts alkylation, meaning we're putting an alkyl group on the ring. We're going to call it a reaction even though the number of cases where it works well is very limited. There's a couple of reasons for that. One, we're generating a cation on carbon, and in many cases we would want sort of like a straight chain, you know, an ethyl, a propyl, a butyl group attached directly. This isn't going to work. We'll be talking about a primary cation. As you recall from back in chapter 7, primary cations, even secondary cations, will rearrange if you give them the chance. And so you'll end up attaching something you didn't want there. And we don't want that. That's a bad thing. We don't want to end up with mixtures. We don't want to end up with reactions that don't work cleanly. We like to control our reactions. So there are a few cases where it works well. The rest of the time it's completely out of control. Methyl groups actually tend to work okay, but now we haven't dealt with this issue just yet, but we have a problem there in that the reaction itself tends to create something that is more reactive. The product of a Friedel-Crafts alkylation reaction is more reactive, meaning that it's going to work faster than your starting material did when the next reaction comes around, when the next amount of reagent comes around to play with. Your starting material is going to lose. So you're going to end up with one aromatic ring with multiple alkyl groups on it and run out of material before you get what you really wanted. So it's a difficult reaction to control. I'm going to put it up here as if it's easy to control just so you see what really happens, and then we'll talk about the electronics of it once we get past the acylation and into directing group effects afterwards. First and foremost, again, we have to use a Lewis acid to manage this. Protic acid doesn't work. We use a Lewis acid with this, and much like what we saw for the halogenation, we see a weakening of that halogen bond. In this case, it's the carbon to halogen bond instead of a halogen to halogen bond. That makes the carbon, in this case, susceptible to attack by the ring, and we go through the rest of the mechanism identically to what you saw for the halogenation. When the aromatic ring attacks that pseudo-cation, or real cation, the carbon, the Lewis acid complex is jettisoned off, and we have a new carbon-to-carbon bond form. After this comes back around to regenerate the aromaticity, we have the reformation of the Lewis acid. It's a catalyst. It comes back in to do it again. Now here's our problem. The product is more reactive than the starting material. That's sort of unsurmountable in this fashion, which is why we come to the next variant, the Friedel-Crafts acylation. Okay, now let's look at the Friedel-Crafts acylation. Now this reaction manages to get around the limitations of the alkylation because rearrangement is impossible. Here we don't have any way that this could rearrange to give another product because it's actually adjacent to a carbonyl. There's no rearrangement possible here, and as a bonus, it cannot react a second time. The product cannot react a second time under these conditions. So we get around rearrangement, and we get around the problem of multiple alkylation because acylation cannot undergo a second reaction. Here's how it works. Same as the alkylation. We have a Lewis acid complex formed with the chlorine of the acyl chloride, weakens that bond, gives us our attack point. In this case, because of the carbonyl, we can even go ahead and break that off entirely and consider this actually just as a single carbonyl attack. After we get our electrophile, again, same deal as always, aromatic ring attacks. Something comes in to act as a base, in this case, As before, it will be the Lewis acid complex. That regenerates the aromaticity, and we're back to our aromatic ring, now conjugated with a carbonyl. Useful trick because we have some transforms we can do on that carbonyl. We can get rid of it entirely, replace it with 2 hydrogens. That gets us our alkyl group if we needed one. We can oxidize it even further, which gets rid of the alkyl group attached to the carbonyl and give us the carboxylic acid. Or we can build off of it using all of the carbonyl chemistry that we'll spend most of the rest of this course on. So a very powerful transform and a very good example of having an alternative strategy to put a certain bond that you want in place. The alkylation is inherently limited. The acylation, albeit slightly slower and more difficult, is not subject to those same limitations. It can get past the problem. That's the whole core of organic chemistry, the whole core of organic synthesis, and for the most part, the whole core of life. Get around the problem.